Hello, everyone. My name is Rob, and I'll be introducing our group's presentation on distributed system concepts. Included in this presentation, we'll discuss an introduction to distributed systems, the major distributed system models, how computers communicate over a network, and how they use these communication protocols to synchronize their clocks in order, use them for critical section protection techniques, coordination techniques, as well as discussing modern distributed system principles. What is a distributed system anyway? A software system that consists of a set of machines that are accessed over a network that are called nodes. These nodes communicate using standardized message passing protocols, and they do not share any hardware. The workload in these machines is distributed so that they can all accomplish a single task or provide a service. The benefits of using distributed computing is that these systems exhibit increased system performance, are more reliable, and are easily scalable due to the fact that there's not a single point of failure and that you can add new nodes to the system. The pitfalls of your distributed computing is that there's difficulty scheduling when a node should provide a service, and there's latency in communication amongst the nodes, as well as problems in monitoring the status of components due to the heterogeneity of the hardware. Distributed systems are used in many cases, in online banking, in video streaming, in video gaming, and in online shopping. Distributed system models come in three major flavors. Client server, the architecture is designated so that there's one server node that coordinates all the secondary nodes' tasks. Peer-to-peer architecture, where these nodes communicate directly with each other. And N-tier architecture, where there's a hierarchy in terms of the nodes that provide different functions. Usually this is because there needs to be a level of confidentiality in the data. In a client-server distributed system, we arrange the nodes so that there's a server or multiple server and many clients. Server nodes run code that coordinate the other components, and client nodes respond to requests from the server and are usually what the user interacts with directly. An example of a client-server distributed system is Netflix. Netflix sends data to client nodes, which is the movie data, and then that manages the clients as well, like updating and logging their information. And then the client is what the user interacts with. It requests the data from the server, receives and formats the data, and responds to the user. In a peer-to-peer distributed system, these nodes communicate directly amongst themselves to complete these tasks. There's no functional differences in the code, and they can all perform the same functionalities. The content and storage, in many cases, is shared amongst the machine. An example of peer-to-peer distributed systems is World of Warcraft. Blizzard uses this distributed system technique to send and parse the data, but even in this case, they designate a master or a host node. The difference is that these hosts can be decided at runtime, and they all retain the functionality to become the host. In an N-tier distributed system, it's mainly used for data security and maintainability so that they can break up the function of the system into maintainable components. The differences in each node are the code and operating system function at each layer and the service that they provide to the system. An example of an N-tier distributed system is Google Drive itself. Hypothetically, they could only need three tiers. Tier 1 is the client, and it's what presents the data and how the user interacts with the data. Tier 2 is the control, which is responsible for the user authenticating themselves and encrypting their data. And Tier 3 is where the database is stored and performs all the requests for creating, accessing, and altering the data. So this would be an example of an N-tier distributed system.
In this section, we will be moving on from how computers are arranged and built to how these machines work with networks. How do the computers communicate over a network in the first place? Let's begin with the basics. A network can be either wired or wireless. The most common network types are known as local area networks, abbreviated as LAN, or wide area networks known as WAN. For LAN, users are connected by common hardware, such as the same internet router or a wired connection. For WAN, users are connected solely through wireless technology. However, networks require standardization in the form of protocols. These are agreed upon templates of how messages passed between machines will be formatted, which includes hardware standardization. Any machine that is part of a network requires any combination of basic networking hardware. This includes routers, hubs, switches, gateways, and network interface cards. The International Standards Organization, the ISO for short, developed the Open Systems Interconnect model in 1981. It consists of functional layers that provide the basis for communication among computers over networks. This core framework of the OSI model is still in modern use. Now we'll take a deeper look into the hardware of a computer. Let's focus in on the first 4 layers of hardware and software levels that are in place to provide communication for computers in a network. Going back to the basic networking hardware we briefly touched upon in a previous slide, let's begin with the network interface card/module. It formats data that will be sent over the network to the specified protocol and connects wirelessly or through a wired Ethernet connection to hubs, switches, routers, or gateways. It involves protocols such as IEEE 802.3, EIA RS-449, and Token Ring. Now for hubs and switches. They are needed to create a local wired network, but are not needed for a completely wireless network. They involve the same IEEE 802.x standards, and hubs route to all connected devices, whereas switches can select which devices to connect to. They can connect to either a gateway or router. Speaking of routers, they're more sophisticated than hubs and switches. They connect multiple devices/networks through a single coordinating device. They also assign IP addresses and are needed for wireless internet. They can connect to a gateway using protocols like IP and ICMP. Gateways join networks by making conversions between protocols. They allow data transmission from one network to another and utilizes protocols such as GGP and TCP. As for the IEEE 802.3, otherwise known as Ethernet, is a physical hardware standard that was developed in 2003 by the Institute of Electrical and Electronics Engineers. It went through several interactions that included support for higher powered devices. In order to connect devices from different manufacturers, computer engineering standards have adopted this modern design protocol. IEEE 802.11 protocol is a direct adaptation of this hardware standard, yet implemented in a wireless transmission circuit. Now, how do computers send messages? Well, modern internet architecture is based on a set of fundamental protocols that were developed in the 1970s and eventually adopted in 1983 by the DARPA. These are the Transmission Control Protocol/Internet Protocol. TCP organizes data to be transmitted between server and client, while IP is the method of actually sending that data from one device to another. It consists of 4 layers: data link, internet, transport, and application. Similarly, the Unified Datagram Protocol, the UDP, can be used to organize transmitted data, and is different only in the information required to create the packet. Now for the message sending protocols. The IP relies on specific protocols to send messages, specifically the ones below. ICMP, created in September 1981 as part of RFC 792. GGP was first outlined in 1982. This is how gateways, the network connecting devices, are able to communicate. They are able to pass datagrams to one another through internet modules. The systems that implement these protocols add the specified information for transmitting this information. UDP and TCP are extensions of IP. Where IP is how the machines are identified, UDP and TCP are formats that ensure delivery of messages and recovery of data. Now for how computers send information. Each IP packet consists of a header and a payload. An IP header is the information at the beginning of an IP packet detailing addressing and routing. A payload is the space dedicated to storing user data. ICMP headers begin right after the IP header above and is identified by IP protocol number 1. All ICMP packets have 8-byte headers. The first 4 bytes are fixed format, the last 4 bytes depend on code of the specific packet. There are 3 classes of IP addresses. Class A, high order bit is 0, next 7 bits are network, and the last 24 bits are local address. Class B, high order 2 bits are 10, next 14 bits are network, and the last 16 bits are local address. And Class C, high order 3 bits are 110, next 21 bits are address, and the last 8 bits are local address. The internet is a large distributed system if we take into account the different hardware components and software protocols as the system.
Clock synchronization and ordering techniques are required for distributed systems because they have time-sensitive requests, and these time-sensitive requests can expire. The tasks also may need to be appropriately ordered in the system, and this is all in the name of creating fault-tolerant systems so that we can accurately display a consensus amongst the systems. The main clock synchronization techniques involve using either a single reference point in the centralized case, or by calculating this information amongst the machines in the distributed case. The first distributed clock synchronization technique was created by David L. Mills, called time protocol in 1983. This protocol establishes a reference time, which is the number of seconds since January 1st, 1900, and will serve as the base until 2036. Although it expires at one point, he also developed Network Time Protocol in 1985, which is built off of UDP-IP format. This protocol provided a template for sending messages, which includes 4 timestamps: the originate timestamp, the received timestamp, the transmit timestamp, and the local time the NTP message is received. Some problems with this algorithm include that we can only compute the skew between the 2 clocks using an algorithm called Christian's algorithm. We need to know more about the machine's clock in order to know which one is actually needed to be adjusted. However, this algorithm is still good for syncing devices where the literal time can be neglected for the relative time. A centralized clock synchronization algorithm is known as the Berkeley algorithm, which was developed in 1989 by 2 researchers at the University of California. In this algorithm, they designate a master node that is known to have an accurate time clock, and this has all other nodes request this time of the master node, which responds with the information on how the computer can adjust their clock. This brings us to the idea of ordering. What really matters for distributed systems is the idea that all events need to be agreed on in the order that they happened. Physical time between the systems could introduce time delays that is not negligible, and the clocks could be desynced amongst the system. So what really matters is the order in which the events happened overall, relative to each other. This introduces the idea of Leslie Lamport's logical clocks in 1978, where machines reach a consensus of the order of events in a distributed system by using a happens before principle. The logic goes as follows. If A and B are events in the same process or machine, and A comes before B, then it follows A implies B. And if A is the sending of a message by one process, and B is the recipient of the same message by another process, then A also implies B. And if A implies B and B implies C, then A implies C. We can see this algorithm in action when we take 3 out-of-sync machines, A, B, and C, and put them in sync using this algorithm. More on this, the algorithm works with vector clocks by introducing an array to keep memory in this equation. It adapts this Leslie Lamport's algorithm directly, where process 1 increments its clock 1 tick, process 1 sends the message to process 2 and includes that timestamp, and then process 2 only adjusts its clock if it's logically correct. Vector clocks introduce memory into this equation by keeping an array called the virtual clock, where each indice is the number of events that have occurred before it stored in a cell. For a 3-process system, each process has 3 arrays corresponding to each other's process and their own, known as VC, virtual clock, I, corresponding to computer I, with indice j corresponding to computer j. This indice returns an integer value equal to k, which is the number of events that have happened before. This can be visualized in the following photo, where we see three processes, each with an array, which is the number of events that have happened in the other processes, which is sent along with the messages. This helps the computers accurately compile packet information and to reach a consensus among the order that events happened.
Hi, everyone. My name is Kieran, and today we're going to be talking about the different protection techniques that critical sections implement in order to protect the resources within. So let's start off with what a critical section is. Basically, it's a segment of code in a program that contains shared resources that are accessible by all the other processes at the same time, as you can see in the picture in the bottom right of the slide. And these resources that are contained within the critical section must be protected to avoid concurrent access from multiple processes at the same time in order to avoid things getting a little crazy. So there are several requirements that ensure that that only one process can access a critical section at a time. And those are mutual exclusion, which by definition means no more than one process can execute the critical section code at one time. There's bounded waiting, which puts an upper limit on the number of times the other processes in the distributed system can enter their own critical sections. And then there's progress, which basically means that if a process is not using a critical section, it should not stop or hinder any other processes from accessing it. So the main protection technique that we're going to be talking about is Lamport's algorithm, which is a permission-based algorithm proposed by Leslie Lamport, and it illustrates a synchronization scheme for distributed systems. There's a picture of it in the middle of the slide. It's explained a little better in the next slide. But basically, there are three types of messages. There's a request, a reply, and a release message. The request asks permission to enter the critical section and is tracked by each process's request queue. The reply sends the permission status to enter the critical section, and release sends a message once exiting the critical section. So continuing with Lamport's algorithm, as you can see, the slide is a bit wordy, so hopefully the picture in the top right helps explain it alongside my explanation. But basically, it's defined by 5 rules. When the first process puts out a resource request, it has to do so by placing a resource request message on its ready queue with a timestamp message. The next process, when receiving the message, places a timestamped acknowledgement message on its queue. In order to actually release the resource, all outstanding resource request messages have to be removed, and then a release resource message that is timestamped is sent and broadcasted to all of the other processes. In order for the process to actually be granted the resource from the initial resource request, these two conditions have to be met. There has to be a resource request message that is ordered before any other request on the queue, which shouldn't be a problem because the algorithm uses permission-based ordering. And the first process also has to have received a message from all of the other processes that came after the initial resource request. So I'm going to be talking a little bit more about a couple other accepted solutions to critical section problems. They're all trying to do the same thing, and that's maintain consistency of data variables and resources across distributed systems to help with process synchronization. So basically, there is Peterson's algorithm, which is in the top right, which alternates between critical and remainder sections. There's Peterson's variation, which is Peterson's algorithm, but with a test and set instruction implemented and the rest of the program changed accordingly. There is a semaphore solution, which uses semaphores, which are integer variables, to solve the problem using the wait and signal atomic operations. And then there are mutex locks, which help the program acquire a lock before entering a critical section and releasing a lock when exiting a critical section in order to prevent concurrent access to the critical section. So just to expand on the last two solutions for critical section problems, I wanted to talk about the semaphore solution and the mutex lock solution just a little bit more. So the semaphore solution, which you can see on the picture to the left, basically it uses the wait operation to decrease the semaphore if it's positive. But if it is less than or equal to 0, it does no operation. This is to ensure that if it's true, it prevents the system from hanging forever. And then mutex locks, as you can see for the picture on the right, are controlled by hardware using the atomic test and set operation. And they are actually platform dependent due to the possibility of hardware variations from system to system. And it uses busy loops, which block processes in the acquire phase, and they're called spin locks.
Hello, everyone. My name is Sibi, and I'm going to be discussing coordination techniques in distributed systems. Distributed systems are especially prone to faults due to the heterogeneity of the system. There are several times when the system may need to be accurate with the value system-wide, and this is particularly emphasized when we have tasks completed where there must be an agreed upon value, tasks completed when there must be an agreed upon decision, or just in general when it is valuable to provide reliability in a distributed system where some machines could be considered unreliable. Coordination techniques are backed up with consensus algorithms that provide us with solutions to these decision-making issues in a system of nodes. As we will discover, when a system of nodes grows larger in terms of nodes, the decision-making issues become harder and the solutions to them also become increasingly difficult. As a result, we will explore both leader-based coordination and the Paxos consensus algorithm. To begin, we will talk about leader-based coordination algorithms. These are popular in blockchain technologies. Blockchain itself is a distributed ledger system, but it essentially acts as a distributed system as well. So the algorithms that go into these technologies do make sense in the course of consensus algorithms. To describe it, a node in the network is made to be the lead node, and it is used to decide on a final consensus. The lead node in this case must ultimately decide on a consensus based on the information received from the other nodes. There are drawbacks to this algorithm though. It is extremely prone to DDoS attacks or distributed denial of service attacks. In this scenario, a corrupted node will target the leader node and send it large packets of information, causing it to shut down. Now, let's say your system is built so that the lead node can continuously switch from node to node. This still may not be a solution because if a corrupted node can target one leader, it may essentially play follow the leader until it gets every node in the system down, causing the entire system to shut down. There are also questions of fairness using a leader-based coordination algorithm. Dependent on its use, whether that be for blockchain, ordering transactions on the chain, or adding blocks to the chain, it essentially increases the reward for a particular node, and if bribed, the lead node does get to make the final decision. Additionally, in another area, let's say the stock exchange market, a lead node could be bribed based on the transaction timing of one node compared to its rival node. Next, we will talk about the Paxos consensus algorithm. The history behind this algo is that it was developed by Leslie Lamport in 1989 as a set of consensus protocols to ensure that machines can reach a decision based on the majority of reliable nodes in a system being available. The description of this is as the design is split into 3 phases, including a prepare, accept, and commit phase. The nodes involved are described as proposers, learners, and acceptors. The idea behind the protocol is to go through a 2-phase process in which the proposers, tagged with a numerical ID, are in communication with the acceptors at each phase. During each phase in Paxos, the most valuable quality is that a majority must be established in order to make a decision. A large part of what makes Paxos a robust consensus algorithm is that it accounts for node failures at any point in the consensus process. This is with the assumption that no node in the system is acting maliciously, which makes the algorithm all that more impressive. To go into greater technical detail about what the Paxos algorithm does, we will break it down by steps. In the first step, a proposer node sends a request to the other nodes called acceptors to complete a task. The acceptors send back a promise message with a timestamp. It is possible it has already accepted the proposal, in which case it just sends the proposal back. The proposer takes these responses and updates the proposed value if applicable, then sends an accept message to all acceptor nodes. The acceptor nodes then update the value to be changed if applicable, and sends the message of acceptance back to the proposer. In other cases, a learner is used as the last point of acceptance for critical values. The proposer or learner node sends commit messages to all the acceptor nodes to update their values thereafter. Other decentralized voting algorithms are very similar to this. The learner and proposer may be the same node, and in all decentralized systems, every node has the functionality to be an acceptor, proposer, or learner. Many times what will cause an acceptor node to not promise or ultimately not accept a proposal is if they have seen another node already request to complete the same task with a larger associated ID value.
Hi, everyone. It's Kieran again. And this time I'm going to be talking about modern distributed systems principles. So by definition, modern distributed systems all contain the following characteristics and principles that I'll be talking about on the next couple slides. There is resource sharing, there is concurrency, fault tolerance, openness, scalability, and transparency. Resource sharing is the ability to use any hardware, software, or data anywhere in the system. And it allows us to control access, concurrency, and provides us with a naming convention, as you can see in the picture on the top right. It's a little blurry, but the picture in the bottom left is supposed to represent concurrency, which basically means components are expected to execute in concurrent processes at once, and it must access and update shared data, variables, and resources. The next 2 defining characteristics are fault tolerance and openness. As you can see, fault tolerance on the top left, it just means that you must maintain availability regardless of the current reliability situation. So if there's some kind of error or anything that makes the system either go down or unable to access, it provides a availability, and it's achieved by redundancy and recovery protocols. Openness is the ease of integration with new components and dealing with any interface type mismatches that occur. So the last 2 characteristics are scalability and transparency. Scalability is solely concerned with the ability to accommodate more users and respond faster. So that means that, if you're designing a prototype and releasing it to the general public, you have to scale that in order to match the size increase that comes with opening up yourself to the general public. The components should stay the same regardless of how many people you have to handle. And then there is transparency, which is described on the bottom left a little bit. And it represents various properties distributed systems could have. And it basically preaches that distributed systems should be perceived as one whole system instead of separate but cooperating components.